Hello, in this video I'm going to be solving problem 46 from section 14.17 of James Stewart's Calculus Early Transcendentals, 9th edition. This problem, which is on the section on finding maxima and minima of functions, asks us to find the points on the surface y squared equals 9 plus xc that are closest to the origin. Okay. So, what do they want? They want us to find the points that are closest to the origin. And so already, this phrase that I've underlined right here already tells us the thing that we need to minimize. So, let's suppose x, y, z, or let me write this. So suppose x, y, z is on the curve, or surface rather, is on the surface, y squared equals 9 plus xz. Then the distance from this point to the origin well, this is nothing more than d. D equals the square roots, and because it's the origin, the distance formula has a particularly simple form. So it would be x minus 0, quantity squared, and similarly for y and z. But because the origin is just 0, 0, 0, we get this simple form right here. And so what we want to minimize is d, where we're given that y squared is 9 plus xz because our point xyz has to lie on that surface. Now, if you try to do this minimization problem directly, like from this, or actually, let me first add a little comment. So, since y squared is equal to 9 plus xz, our distance, just by plugging in that y squared right here, we can write this as x squared plus 9 plus xc plus c squared. And so then our problem would be to minimize the function, or I'll add that in a bit. So we want to minimize this. But if you tried to do this minimization problem with this function of x and z directly with the square roots, the partial derivatives you need to calculate become really ugly. And we can make our lives a lot easier by instead making this very nice and clever observation. So since the square roots function is strictly increasing, the minimum of d is the same, occurs at the same place as the minimum of the inside. And by inside, I just mean everything inside of the square root. So f of x z equals x squared plus 9 plus xz plus z squared. And so this makes our problem a lot easier, because if we can find the minimum of this function right here, whose derivatives are much easier to calculate than that if we had included the square roots, then we just need to plug whatever location we get for this minimum. Because of this fact about the square roots, that it's increasing, strictly increasing, we'll know that the minimum of the distance up here will occur at exactly the same place. And so the points that minimize the distance here from the origin to our surface will be exactly the same points that minimize this function right here. Now recall that the minimum of a function always occurs at a critical point. And these critical points occur at where the partial derivatives are equal to 0. So let's compute these partial derivatives. So partial with respect to x is just 2x plus z, and this needs to be 0. And similarly, partial of f with respect to z now, this is just, I guess you could write x plus 2z. And we also need to set this equal to 0. And so what we get is this system of equations that we need to solve. And this isn't so bad because, for example, if we solve for x in the second equation, x is going to be negative 2z. And so plugging it in to the first equation, we get 2 negative 2z plus z equals 0, which says the same thing as negative 4z plus z equals 0, i.e. negative 3z equals 0, which has only the solution z equals 0. And so then if we take z equals 0 and plug it in over here, we see that x also has to be 0. And so the only critical points of our function is the point 0, 0. Okay. And now, once we have this critical points, we need to go back, and because remember that the problem asked us for the points on the surface that minimize the distance. So because we want them to be closest to the origin, but our surface is y squared equals 9 plus xz. And so because x and z are both 0, we can find the y coordinates. So points closest to origin. Well, to find these, we just need to remember that y squared is 9 plus xz. But our critical points at our only critical point of f, both the coordinates are 0, and so when we plug these in over here, we get that y squared is 9, so y has to be plus or minus 3. And therefore, the critical points are 0, 3, 0, and 0, negative 3, 0. And to show that these are indeed the points that minimize the distance, let me pull up a graph from Desmos 3D and show what the points look like relative to the surface. Here I have Desmos 3D out, and I've plotted our surface, and it's a really nice surface right here, and we can see that the origin lies at this point. Now, just looking at this side view of the surface, hopefully it's apparent that the points that are closest to our surface should lie along this diagonal cross-section right here, because these are the ones where the distance from the origin here out to the edge or the surface itself is minimized. And if we turn to another cross-section of our surface right here, we see that that slice is actually this ellipse-looking shape right here. And just from looking at this ellipse, we can see that this axis and this axis are longer than these two axes. And so we would guess that the points that we just calculated correspond to these points of our ellipse. And indeed, when we plot these points, we see that they are exactly those 2 points, just as we have calculated on the notes previously. Okay. This wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.